Hello everyone. Welcome to this fourth video lecture on 8051 microcontroller. In this lecture we will be seeing how to program time delays in 8051 microcontroller using timers. More specifically, we will be discussing the timer implementation using interrupt method. This lecture is prepared for the benefit of students and other learners who are interested in knowing about the working of Intel 8051 microcontroller, its interrupts and its timers. Some of the prerequisites are theoretical knowledge about the 8051 microcontroller hardware architecture and its special function registers. Delay generation using 8051 timers and the modes of operation of the 8051 timers were discussed in the previous two lectures. You should have theoretical knowledge about the 8051 interrupts and associated special function registers in addition to basic 8051 assembly language programming. Also, EdSim51 simulator was introduced in the first lecture. You may refer the earlier lectures. The topic of today's discussion also includes the interrupts, vector addresses and special function registers associated with 8051 interrupts.
We will focus on the interrupts associated with 8051 timers.
After this, we will write delay subroutines using timers by interrupt method. Next we will interface LEDs to 8051 microcontroller and write assembly language program to blink them at regular intervals. For this we will be using the delay subroutines that we have written. After this we will copy this program to the 8051 simulator and run it to see its working. This lecture closes with an exercise question as an assignment. We can define interrupts as internal or external signals to a microcontroller that instructs it to execute a particular task. When an interrupt occurs, a hardware call to a particular address occurs. Here a subroutine called interrupt service subroutine or in short, ISS is written. Interrupt service subroutine is similar to a normal subroutine except that the subroutine call is hardware generated and also it modifies the corresponding interrupt flags. Also the last instruction of an interrupt service subroutine is GRET instruction. Now let us try to understand vector addresses. Vector addresses are memory addresses to which the program control is transferred to at the time of occurrence of an interrupt. This is possible by loading the program counter with the corresponding vector addresses. The following table shows the various 8051 interrupts and their corresponding vector addresses. Reset interrupt is having the highest priority here. You should note the following points while working with interrupts in your programs. This is because the vector addresses are fixed. So start writing other programs skipping these locations. Also, as you can see only few bytes of memory are available between these vector addresses. So here we will be placing only an LCALL instruction to the corresponding interrupt service subroutines. Also like discussed in an earlier lecture, you should take care of the stack memory to avoid data corruption. This slide shows the special function registers associated with 8051 microcontroller interrupts and timers. Interrupt enable special function register, i.e., contains the EA bit. This is the enable bit of the other interrupt bits. Also we can see the enable bits for the various interrupts. Setting a bit in this special function register enables the interrupt bits or the corresponding interrupts. The other special function register associated with 8051 microcontroller interrupts is the interrupt priority special function register, IP. This special function register is used to modify the default interrupt priorities. This is very useful when we write programs for applications in which multiple interrupts may arise at the same time. In our present discussion we will not be doing this. Rather we will go with the default interrupt priorities. Because we are dealing with only timers here. But you have to note that T0 interrupt is having higher priority than T1 interrupt because of the default polling sequence.
We have already discussed about the timer special function registers TCON and TMOD in the previous lecture.
However, you should note that the flag bits TF of TCON special function register will generate the corresponding timer interrupt signals. This flag is cleared automatically when the corresponding interrupt service subroutine is invoked. Next we will see how the 8051 timer counter module is used to generate time delays. Here we will be discussing the interrupt method. We know that the counter register of the 8051 timer counter module receives a clock signal that is 1/12 of the CPU clock. For example, if we are using a 12 MHz clock, the counter register increments at the rate of only 1 MHz. That is, a counter increment requires 1 microsecond. Hence, suitable time delays can be obtained by loading a count value to the counter registers. And whenever the counter overflows, that is, there is an overflow from FFH to OOH for 8-bit counter operation, or there is an overflow from FFFFH to OOOH, the timer flag TF is set. At this time, the timer interrupt signal is generated and the program control is transferred to the corresponding timer interrupt vector address. When compared to the polling method, this method is better as the CPU need not check TF bits periodically or remain in an idle wait cycle. Okay, now let us see the steps involved in programming the 8051 timers. Here we will be discussing the interrupt method for programming the timers. We will broadly divide this method of programming delay into 4 steps. They are configuration, initialization, the starting and stopping of the timer counter modules, and the interrupt service subroutine. Let us examine in detail each of these steps. In the configuration step, we will clear the gate bit and then set the counter timer operation selection bits. Also, the M1 and MO bits are set or cleared for the desired mode of operation. In this lecture, we will be concentrating only on mode 1 operation of the timer counter module. Discussions on mode 0, mode 2 and mode 3 operations will be done in a different lecture. So for mode 1 operation, both M1 and MO bits should be cleared. The next step is initialization. In this step, we will clear the TR and TF bits of the TCON special function register. Also, we will load the initial count value to the TH and TL counter registers. Now the third step is to enable the interrupts and start the timer. First, the interrupt bits are enabled by setting the EA bit of the IE special function register. Now we can use the interrupt bits by setting the corresponding interrupt enable bits of the IE special function register. In this case, we are enabling the timer interrupts by setting the ET1 and ET0 bits respectively for T1 and T0. After this, we start the timer by setting the TR bit of the TCON special function register. Once the timer starts running, the timer overflow flag bit TF will be set when there is a timer overflow. At this time, the timer interrupt signal is generated and the program control is transferred to the timer interrupt vector address. Also, the timer still continues to count from 0 onwards after overflow. So either we have to stop the counter or reload it with correct initial value. These things have to be done in the interrupt service subroutine. Inside the interrupt service subroutine, we will first clear the EA bit of the IE special function register. This will temporarily disable all the interrupts for the duration of execution of the current interrupt service subroutine. After this, if required, the timer is stopped by clearing the TR bit of TCON special function register. Or if we want the timer to continue counting, then we have to reload the initial count value in the counter registers. Unlike polling method, here we need not clear the TF bit as it will be cleared automatically when the interrupt is serviced. At the end of the interrupt service subroutine, we will re-enable the interrupts by setting the EA bit of the IE special function register. Note that this clearing and setting of EA bit is not done when you are dealing with multiple interrupts and you want another interrupt to preempt the execution of the current interrupt service subroutine. Also, sometimes, we may have to allow the counter to overflow multiple times in order to achieve the required time delay. We can do this by suitably using a counter and writing the interrupt service subroutine accordingly. We will be seeing how this is done. Next, we shall see how to write 8051 assembly language programs for each of these steps that we have discussed. For convenience, we will write separate subroutines for each step. Let us start with timer configuration. You have to note that in this lecture we are discussing about only the timer operation of the timer counter module of 8051 microcontroller. Also, we will be discussing the mode 1 operation alone. In the following subroutine, we will focus on T0 alone. The same logic will apply for T1 also. Now, we will write T0_config subroutine to configure T0 to operate as a timer in mode 1 operation. For this, we will move the following binary value to the TMOD special function register as shown. Since only the lower 4 bits of TMOD special function register are used by T0, the higher 4 bits are shown as don't care conditions here. If you want to configure T1 also, then we can put suitable binary values in place of these don't care conditions. For now, you can assume zeros here. In the previous lecture, we have already discussed a method on how to modify only a few bits of a bit addressable special function register without disturbing the other bits. You can implement that method here also. Next we shall see the subroutine for initializing T0.
We will write T0 underscore init subroutine for this.
The timer is stopped first by clearing TR0 bit. And also the T0 overflow flag TF0 is cleared. Then we will load the proper initial count, that is, count 1 and count 2 to the timer counter registers TH0 and TL0 respectively. The values of count 1 and count 2 variables will depend on the time delay required.
We will write T0 underscore start subroutine to start the T0 timer.
For this the TR0 bit is set. Also in this subroutine will enable the interrupt bits by setting EA bit and enable the T0 interrupt by setting ET0. The T0 interrupt service subroutine T0 underscore is written next. In this subroutine we will disable all the interrupt bits by clearing the EA bit. Then we will write the required code for executing the task at the time of interrupt. After this the interrupt bits are re-enabled by setting the EA bit. You may note the RETI instruction being used at the end of this interrupt service subroutine. Now we will take a problem in which 1 millisecond delay is required. Assuming 12 MHz clock, we have already discussed that a counter increment requires 1 microsecond. So we need a total of 1000 counter increments to generate 1 millisecond delay using timer. So we calculate the initial counter value as shown by subtracting number 3E8H from FFFFH to get OFC17H. Now the higher byte of the count is loaded to TH0 and the lower byte to TL0. The counter will now start incrementing this value with every 12 clock ticks, that is, 1 microsecond. Now we will write the assembly language codes for initializing T0.
We will write T0 underscore init underscore 1 millisecond subroutine for this.
Here we will stop the timer and clear the timer flag. Also, we will be loading the initial counter value to the timer counter registers.
We have already discussed these steps.
Next we will write a subroutine, delay 1 millisecond. Here we will call the already defined subroutines, T0 underscore config for configuring T0 as a timer in mode 1. The T0 underscore init underscore 1 millisecond is called for initializing the timer. And the timer is started by calling the T0 underscore start subroutine. You must have noticed that we don't have to define a wait subroutine like in the polling method. Next we will take the case of a 1 second delay. Here also we are assuming the 12 MHz clock. And we know that 1 second equals 1000 milliseconds. So we need a total of 1 million counter increments. But we know that a 16-bit counter can count a maximum of only 65,535 count, that is, approximately 65.5 millisecond. So we have to run the counter multiple times to generate 1 second delay. In this example we will initialize the timer counter value such that we can generate 50 millisecond. For this we will write T0 underscore init underscore 50 milliseconds subroutine. Then we will call this subroutine 20 times in another subroutine called delay 1 millisecond. The initial counter value for 50,000 microsecond, that is, 50 millisecond is calculated as shown to be equal to 3 CAFH. This slide shows the 8051 assembly language code for defining T0 underscore init underscore 1 subroutine. Just as discussed before for the 1 millisecond subroutine, here also we will stop the T0 by clearing TR0 bit and clear the timer flag bit TF0 before loading the initial count value to the T0 counter registers TH0 and TL0. Also we will use R2 as a counter register and initialize it to number 20 in order to count the number of counter overflows. Now we will write delay underscore 1 subroutine. Here we will call the already defined subroutines T0 underscore config for configuring T0 as a timer in mode 1 and T0 underscore init underscore 1 that we have defined just now. Also, the timer is started by calling T0 underscore start subroutine. Next we have to write the subroutine call instruction for T0 underscore is interrupt service subroutine at the timer interrupt vector address 0BH. Inside the interrupt service subroutine, the interrupt bits are disabled by clearing the EA bit and the initial counter values are loaded to the T0 counter registers TH0 and TL0. Next we decrement the counter register, R2. After each decrement we have to re-enable the interrupt bits and return until R2 becomes equal to 0. Since the timer is continuously running in the background, the next interrupt will happen when timer overflows again. This will be exactly after 50 milliseconds. When R2 becomes 0, 50 millisecond would have elapsed 20 times and the total time delay would have become 1 second. Remember that we have assumed a 12 MHz clock here. Now the first exercise that we are going to do is to interface an LED to the 8051 microcontroller. Then we will write an 8051 assembly language program to blink this LED every 500 millisecond. The 500 millisecond given should be taken as the LED on duration only. Further, we will assume 12 MHz clock and 50% duty ratio. In the previous two lectures we have discussed about the significance of delays while blinking LEDs as visual indicators. A phenomenon called persistence of vision limits human eye to detect sudden transitions. So we need delays of the order of 50 millisecond and above in such applications. However, faster light pulses at different wavelengths and intensities can be used for communication technologies using visible light such as Li-Fi, OFC, etc. This figure shows how the LED is interfaced to the 8051 microcontroller P1.7 pin. You may notice that for this connection, making the P1.7 pin low will turn on this LED. Next we will write the 8051 assembly language program to obtain the desired functionality. This program clears and sets the P1.7 pin repeatedly at regular intervals to turn on and off the LED connected to it. Delay _ 500 milliseconds subroutine is used to generate the required delay for the blinking action. This is done by counting 50 millisecond 10 times. R2 register is used for keeping the count 10. This is decremented every 50 millisecond. Since we are programming timers using the interrupt method, the toggling of the LED is written inside the interrupt service subroutine T0 is. Inside this, we will also reload the initial timer counter value and decrement the counter register R2. After each decrement we have to re-enable the interrupt bits and return until R2 becomes equal to 0. Since the timer is continuously running in the background, the next interrupt will happen when timer overflows again. This will be exactly after 50 millisecond. When R2 becomes 0, 50 millisecond would have elapsed 10 times and the total time delay would have become 500 millisecond. This is the complete program for the given exercise question. See how the interrupt vector address spaces are bypassed by using the LJMP instruction at hexadecimal 0000. Next we used LJMP T0_is at the T0 vector address hexadecimal 0000B in order to jump the control from the vector address to the interrupt service subroutine location. And the actual program is written at roam location starting from hexadecimal 0050. After turning on the LED, we called delay _ 500 milliseconds subroutine. Inside this subroutine, T0_init _ 500 milliseconds subroutine is called. As a result, T0 will be counting 50 milliseconds 10 times. Inside the interrupt service subroutine T0_ is, after reloading the counter, the R2 register content is checked. P1.7 pin will be toggled only if R2 becomes 0. This happens only once every 10 cycles of interrupt. At other times, the interrupt service subroutine T0_is returns only by decrementing the R2 content. You should follow the correct syntax for writing the 8051 assembly language program. Now you can copy this program to the source code pane of the EDSIM51 simulator. Also change the update frequency to 50,000.
We have discussed what this setting is all about in an earlier lecture.
Next you can click on the Run button. You can see the LED at P1.7 getting turned on initially. Now we will wait for the simulation time to reach 500 milliseconds. See, now the LED has turned off. So our program is working correctly and as expected. We will wait for the simulation time to reach 1 second so that a complete cycle is executed. See, now the simulation time has passed 1 second. And we can see that the LED has turned back on again. Further, you can wait to see the next cycle of LED blinking as the simulation time reaches 1.5 seconds. You can also study the variations happening in the registers during each step using the method we have discussed in the previous lecture. Again, the point to be noted is that the output obtained depends on the wiring of the LED and as well as the program written. You can also pause the simulation at the LED transition times and see the corresponding simulation time. In the previous lecture I have pointed out that the simulation times were exceeding than is expected from the delay subroutines we have written. This was because we skipped something there while we were rerunning the timer. This was given as an exercise for you to find out. But in this program we have rectified this. So you will see that the error observed through the simulation time in the previous lecture is absent here. So what was that error that we have rectified here? Think. This explains how slight modifications in the algorithm drastically modifies the output obtained. Now the exercise question that I am going to give you is to interface two LEDs to 8051 microcontroller. Then write the 8051 assembly language program to blink one of the LEDs every 50 milliseconds and with 50% duty ratio. The 50 millisecond given should be taken as the LED on duration only. This has to be considered as a main task. Now the second LED should blink every 200 milliseconds and with 50% duty ratio. This should be the interrupt service subroutine. You have to use timers and timer interrupts and assume 12 MHz clock. The hint that I can give you is that for delay generation you can use both the timers T0 and T1 simultaneously. Use polling method for first LED. Also you will need a counter for counting the number of blinks of the second LED.
We have already seen a method for modifying a single bit alone of a byte addressable special function register like TMOD special function register in the previous lecture.
It is copied here also for your recollection. This video demonstrates the desired output expected from the exercise question given as assignment. We will click run. And the red LED has turned on. We can see that it is turning on and off every 50 milliseconds. And when the simulation time reaches 200 milliseconds, the yellow LED has turned on. This was the interrupt service subroutine expected. We will wait for simulation time to reach 400 milliseconds. Now the yellow LED has turned off. This process is repeating continuously. Try to write the 8051 assembly language code for this. With this we are concluding this lecture on 8051 timer implementation using interrupts. These are the literature and websites from where some of the materials were taken. You can refer them.